Hello everyone, I'm Farnaz Foroughifar from Embedded System Laboratory of EPFL in Switzerland, and today I'm going to present you our latest work in AICAS 2021 titled as Selfaware Anomaly Detection for Epilepsy Monitoring on Low-Power Wearable Electrocardiographic Devices. This work is a result of collaboration between EPFL, Western Norway University of Applied Science, Lund University, and Aarhus University Hospital. So first, let's talk about biomedical wearable systems. So we know that in many pathologies, we need to monitor the patients by using some devices, including one or more sensors, which are attached to the patients and then monitor their biosignals. Then what is important here is continuous pathology monitoring by removing constraints concerning time and location, which is done by using wearable systems. Because using wearable systems, the patients can wear the sensors at any time and any place that they are, so we can monitor them continuously. And what is also important here is that these wearable technologies should be low power. They should be low power because the patients should be able to use these sensors and these devices for a long time without the need to recharge them frequently. And that's what we are going to focus in this work is on the low power aspect of these wearable technologies. So our solution here for making the system more low power is using self-aware systems. So in self-aware systems, we have the system and there is a loop around the system which controls it and tries to make it more energy efficient at real time. So first we observe some parameters from the system so that we can see in what state the system is. And by analyzing these parameters, we see if the system can work in more energy efficient state or not. If it is the case, then we take actions we change some parameters in the system to make it go to the state that it can work more energy efficiently. And then this loop continues as long as the system is working, so that we can maintain the system always in its more energy efficient state. So self-awareness equips the system with control units to facilitate monitoring the performance, adapting to changes, and also improving autonomously based on the goal that we have, like for example, reducing energy consumption in runtime. Then we have our case study, which is epilepsy here. And why we have chosen epilepsy among different pathologies that we have? Because first, epilepsy is affecting more than 50 million people worldwide, around 1% of the world's population. And unpredictable seizures can happen at any time and with a huge impact in the quality of the life of the patients. And also epilepsy is a second neurological cause of years of potential life loss and can also cause SUDEP, which is sudden death caused by epilepsy. So in epilepsy case study, the challenge that we have, which is also true for some other pathologies like epilepsy, is that the attacks occur infrequently. For example, in the data set that we have, just average of 0.1% of the data are attacks and the other data is just a normal data. For example, here we can see a record of one patient and we see in 41 hours of record and data, we just have 2 seizures, the first one with the duration of 41 seconds and the second one with the duration of 149 seconds. So as you can see, the number of samples labeled as attacks and seizure is much less than normal data. So the first solution that is given in literature is data balancing. So they try to use the same amount of normal data and seizure data and use classification methods. But the problem is that this is not generally applicable in realistic scenarios. And because the limiting part is the number of seizure data, at the end, the number of data that we have is very limited. So we cannot train many complex models. So our solution is using anomaly detection instead of classification to model based on non-seizure data. So instead of using 2 labels, we just use non-seizure data here to model our anomaly detection model. But then the problem that we have here is that the anomalies, which are the outliers, can have many different reasons, that one of them is just epilepsy and the seizures. So what we do here is that we also use information from part of the seizures of the patients to have a better model that works better on the seizure data. Now I'm going to talk about our self-aware anomaly detection, which we use to address the problem that I just mentioned. First, I'm going to talk about isolation forest here, which is the method that we use for anomaly detection. So in isolation forest anomaly detection, we want to distinguish between normal data and outlier data. So if we consider the normal data, which is the picture in the left, we see that in order to isolate this data from the rest of the data in the data set, we need many splits. So we should split the data set many times so that the xi is isolated from the rest of the samples. But on the other hand, for the outlier data, which is shown here as XO and is in the right picture, we see that with very few number of splits and divisions, we can isolate this point from the rest of the points. And that's the main difference between normal data and outlier data. So we can say that in the isolation forest, which is based on decision tree, each forest model consists of several trees, which are branched based on choosing one feature at a time and dividing that feature from a specific random point. And also in isolation forest, we assign a score to each input, which shows how quickly and easily it can be separated from the rest. So the points that can get separated from the rest quicker than a threshold that we should define are considered as outliers, and the other data are considered as normal data. Here we see a general overview of the self-aware system that we have. And as you can see here, we have several different models in the system named from model 1 to model M. So these models are different in terms of energy and also error. And as you can see, the model 1, the first model, has the least energy consumption. And although it gives correct answer for most of the samples, for the samples that it does not give correct answer, the probability of having error is the highest. Then we move to model 2, where its energy is a bit higher, but the probability of having error for this model is a bit less. And this continues until we reach model M, for which the energy is the highest, but at the same time the probability of error is the least. So the approach is that we start with model 1 and see if the decision that is made by this model is reliable or not. If yes, then we choose the decision and the flow is finished. Otherwise, we move to model 2 and again see if the result is reliable or not. And then we continue this procedure until we reach the model for which we see that the decision is reliable. And how we can see that the decision is reliable, we will see later. But another thing that we should pay attention to is that the set of the features that are extracted for each model is also different. So as we move to the more complex model, the number of features and the set of features that we should extract is increased. So the energy consumption and the amount of energy that we need for feature extraction is also increased for more complex models. So we have two parts of self-awareness here in this anomaly detection system. The first one is what actually considers the information from the seizure of the patient. So we take the scores calculated for the first seizure of the patient and then compare it with a threshold called S threshold. And what we do here is that if the score of the seizure for this patient is more than this threshold, we say that detecting the seizures for this patient is complex. And this can result to a very high number of false alarms for this patient, which is not desired. So what we do is that for these patients, we just use the first model, which is the most simple model, so it makes the false alarms to reduce as much as possible. And otherwise, we move to our second type of self-awareness, which is multi-level anomaly detection. And how we calculate this threshold, this score threshold, is that for each patient, like for patient I, we take the threshold score for other patients at the point that the false alarm rate is the desired value. For example, if the desired value is R here, like 1 alarms per day or 2 alarms per day, and then we take average of all the patient except the patient for which we are calculating the threshold, and then we have the score threshold for that specific patient. And then we compare the seizure score with this score. For example, in the data set that we have used in this work, if we put R as 2 alarms per day, we see that 17 out of 43 patients that we have actually have a complex detection of the seizure. So for 17 we use just model 1, and for the rest we use the second part of the Selfaware system, which is multi-level anomaly detection. Now I talk about our multi-level anomaly detection. As I mentioned before, we have this error complexity trade-off between different models that we have. And as we know, the less complex models have lower performance, but also lower energy consumption. So we have different models from model 1 to M, and the complexity is increased from model 1 to model M. And then the overall complexity of the system depends on the probability of invoking each model. So we can say that this overall complexity is calculated as summation of multiplication of probability of invoking model I and the complexity of this model. Then we have our multi-level anomaly detection, as I have shown before. Here I want to talk about how we choose if the model is confident and reliable and we should take its decision or not. So we have something called confidence for each model, and the model is confident when the deviation of the scores of different trees is less than a threshold that we define for each of these models in the training phase. And the definition of the threshold of each model and also the confidence is shown here. So first we calculate the confidence for the first model and we compare it with its threshold. If the confidence is more than threshold, then we choose a decision from this model. Otherwise, we move to model 2, again calculate the confidence and do the comparison. And we continue this procedure until we reach the model for which the confidence is more than the threshold. And that means that we can take the decision of this model. Now we are going to see the Selfaware anomaly detection in our epilepsy case study. And here we see that instead of using multi-level anomaly detection for our epilepsy case study, we use two-level anomaly detection. So we have two models, model 1 and model 2, which are also called simple model and complex model. And as you see, the equation for threshold is the same as what we had before. And for alpha, we put values of -1, 0, and 1 to have different probabilities of invoking simple model. And then we evaluate the method on EPatch dataset, which is dataset from Aarhus University Hospital in Denmark, with data from 43 patients, 74 hours of recording per patient, and with data from single lead ECG with acquisition frequency of 512 Hz. And from the 20 features that exist in this dataset, we use 10 features that are shown in the table. And all these features are taken from 3 main HRD methods. The first one is HRD, which is second order central differential calculation of all consecutive hour intervals, CSI, which is cardiac sympathetic index, and MCSI, which is modified cardiac sympathetic index. And we combine these HRD method definitions with pre-filtering and also slope of RR intervals with respect to time. And we have the 10 features that you can see here in the first table. And among these 10 features, we use the 3 more complex features for the simple model, and we use all 10 features for the complex model. Now we are going to see the results of performance and complexity on the EPatch dataset. First, we see the results of the performance. So if we put the number of desired false alarm rates to 2, so R is equal to 2, then we have 3 different scenarios that we will check here. The first one is just using the simple model for all the data. And as we see, the number of responders, which is defined as the number of patients for which our system gives a sensitivity of more than 2/3, which in other words means that 2/3 of their seizures are detected is 21. Then the false alarm rate of these responders is 2.85 per day, and the sensitivity of the whole data set is 59.5. Then we have the scenario in which we just use a complex model for all the patients. We see that the number of responders is increased to 32 patients. Thus, the sensitivity is also increased a lot to 77.9%. But also we see that the false alarm rate is increased to 24 alarms per day, which means like 1 alarm at each hour, which is a lot. So in between also we have the self-aware system, and we see that as we move from simple model to complex model, the number of responders and also the sensitivity is increased. Then we can say that with the first form of self-awareness, 24% increment in the number of responders happens, and with the two-level anomaly detection, the range of responders is changed between 21 and 26. We can also say that moving from simple model to complex model, the sensitivity is increased from 59.5% to 77.9%. Then here we see the results of the complexity of the method on ePatch dataset. We also here see the different scenarios of having just a simple method, having the complex model, and having the self-aware system. And for the complex model, we have the complexity of 100. Then for the simple one, we have the complexity of 30. That's because all the features that we have here have the computational complexity of order of n. And we can also see that using the first part of the self-awareness, the complexity is reduced to 72.3%, and adding the second part, the self-aware system complexity for different values of probability of using the simple model, we have complexities of 65.6, 49.9, and 37.6. So we see that moving from complex model to simple model, the complexity is decreased from 100% to 30%. Now we conclude this work. We have seen that to enable continuous monitoring of patients, we can use the concept of self-awareness, and by using anomaly detection model instead of classification models, we can overcome the problem of lack of seizure data. We saw how we can trade off detection quality with energy and complexity by using multi-level anomaly detection. And then we saw that the complexity of the system could be reduced in range of 72% and 30% depending on the level of self-awareness and confidence threshold that we use. Thank you very much for your attention, and if you have any further questions for any further information and discussion, you can contact me on my email.